round off the day nicely, which is just skip back to chapter 4, which is deterioration of steel structures. Okay. It's not quite as long as the last one, but probably I'll be pleased to know. Yeah. So deterioration of steel structures chapter. So as soon as any piece of engineering equipment is put in service, it'll start to wear out through use. Not maintained, it'll eventually cease to operate satisfactorily, either by no longer carrying out its designed function or by failing in a catastrophic manner. Obviously, we want to avoid. Okay, so deterioration, an offshore structure, is broadly classified into 6 categories: gross structural damage, corrosion and erosion, fouling defects, coating defects, scour, metal, and weld defects. So gross structural damage, deformation due to impact, missing bolts, damage of cabling, cabling ducts, missing members, anodes, etc. Engineers try to anticipate all the different modes of failure. The most difficult to design against is obviously accidental damage. So corrosion, and we'll talk about this quite extensively tomorrow. We have uniform or pitting corrosion. So uniform corrosion is metal loss over the entire metal surface. Pitting corrosion, localized corrosion, rating a pit. Both types of corrosion are accelerated by erosion. That's the basically hard particles or even fluid molecules themselves striking the surface and remove material. Increase in temperature. Again, we'll see tomorrow that the definition of corrosion is it's an electrochemical reaction between a metal and its environment. So with almost all chemical reactions, if you increase its temperature, you increase the rate of corrosion. You increase the rate of that reaction, don't you? Okay. So corrosion is no different. So anything operating at an elevated temperature has the potential to corrode at a faster rate. Okay, so increase the temperature, increase the rate of corrosion. Increase oxygen content. So again, where we said we've got any turbulence. So around a pump, for example, so we'll expect to see more corrosion on the inside of our caisson, adjacent to where the pump is, again because of that turbulence creating more oxygen in the electrolyte. Chemical attack from biological sources, and loading, both external and residual. Okay, so put steel component under a tensile load, and again it'll corrode at a faster rate. Okay. So fouling defects, these consist of both marine growth and debris. And the effects of debris can be structural damage, galvanic corrosion, overloading the CP system, and of course it can be a safety hazard to both divers and ROVs. Coating defects, paint and bitumen. Coatings can have poor surface adhesion, blistering of the coating, flaking, so due to a lack of adhesion, sagging and wrinkling, particularly on thicker coatings, and cracked surface coating. So the whole idea of a coating on a metal surface is to create a barrier and stop the seawater from coming into contact with the metal underneath the steel. Okay. Again, jumping the gun a bit, but tomorrow we'll see 4 things we need for corrosion cell: an anode, cathode, an electrolyte, an electrical connection between the anode and cathode. Okay. So if we put a coating on our steel surface, we exclude the electrolyte, seawater, and we break the corrosion cell. Okay. So the whole idea of a coating: form a barrier, stop the water from coming into contact with it to stop corrosion. Okay. If the coating is damaged in any way, seawater can come into contact with the steel, and we can set up a corrosion cell, and our steel will corrode. Okay. Scour, talking about that. So it's undermining the seabed due to an increase in water flow rates, and metal and weld defects. we'll talk about those probably Wednesday. Okay. So fatigue, again, we covered that this morning. So we said fatigue, local failure of the metal, crack growth caused by cyclic loading. Fatigue causes more in-surface failures than any other mode. Fatigue cracks can grow from flaws in material. They can be initiated in regions of high stress material and start from pits created by corrosion. So they can occur when the applied stress is well below the yield stress of the material. The crack propagates by acting as its own stress razor. The final crack is a result of a great many load cycles, and eventually the cross-sectional area is reduced to such an extent that final failure occurs by rapid fracture. And then again, we said it can either be ductile failure or brittle failure, depending on the nature of the material. So fatigue cracking does not affect the fracture toughness. It's difficult to predict in any material, as a process is sensitive to a number of variables, which will include a number of load cycles, stress amplitude, temperature, the environment, material's microstructure, and the surface condition. So where is thinning a material due to corrosion, erosion, or a combination of both? An adhesive wear is friction between two surfaces. Abrasive wear is when one surface gouges another. Fatigue wear, micro cracks detach particles of material, cause gouges. Chemical or corrosive wear, oxides from that are removed and then reformed. So material may change in its properties from ductile to brittle, and this could be due to incorrect welding procedures, the absorption of gas, generally hydrogen, that has been encountered on natural gas pipelines. Brittle materials fail due to crack propagation, so are also susceptible to fatigue, as well as brittle fracture. And again, brittle fracture is more likely to occur at lower temperatures. So defects may be caused any of the 4 stages in the life cycle of a structure. So production of the raw materials, fabrication, installation, or of course in service. Okay, so look at these. So production of the raw materials. So our offshore structures predominantly made of steel. Steel, as I'm sure you're aware, is an alloy. It's predominantly made with iron, with the addition of carbon and other alloying elements, again depending on the type and grade of steel. Okay, so mix the right quantities of ingredients together, okay, and they should be uniformly dissipated throughout the mixture. Okay, then pour the steel from the crucible to form an ingot. And we can see on this occasion we've got a couple of little bits of liquid metal splashing up onto the side of the mold. That will cool very rapidly, and when the rest of the steel fills up and cools, these won't fuse back into the rest of the block. These will be essentially what's called fishtails or lapses on the surface. Okay. Oops. So when that steel is then processed and rolled out, like I said, these don't fuse back in. Is it a defect that you find in service? Probably not, because we picked that up at the fabrication stage. So wouldn't worry too much about that one. Yeah. Inclusions in the steel. Okay, so that steel is poured in, and then as it cools, any low melting point impurities, they rise up to the surface. Okay, then all that should be collected off. That bit's then reprocessed, and then we should have a good block of steel. Okay, if that liquid metal cools too rapidly, then these impurities can get trapped within the material, and we get what's referred to as banding and segregation. Okay, again, modern steel making processes, we shouldn't be coming across things like this, but you never know. Okay. But again, we wouldn't be able to really tell if we had it unless you cut the steel open, polished it, and did a macro on it. Yeah. These impurities, okay, if we put a through thickness stress on our component, we're going to T-joint, then fillet welded. These impurities can then open up, and we'll get what's referred to as a lamella tearing. Okay, and that crack would have a step-like appearance as it lines up with all those other defects. Okay, but again, not really something you need to be too concerned with. Next one though, laminations. We do get laminations in steel. We find it in steel plate and in pipe. It's laminations in the middle thickness of the material, and it's always in the roll direction of the plate. Okay, and we find laminations very easily with ultrasonic inspection. Okay, so again, casting our steel blocks, we form the material in there, so it's in a liquid form, fills in. Okay, any low melting point impurities again are pushed into the middle. Okay, because obviously the middle's the last place to cool. Okay, and then they get pushed up to the surface. Okay, and then when this block solidifies, we get what's called a pipe. And then again, that's chopped off, and then the steel is then good to go. Okay, but on occasion, and it is rare occasions, we can get a gas bubble trapped in the steel block. Okay, so the steel is then tipped out onto its side. Okay, we've got that gas bubble in there. Okay, steel is then rolled out, and then it becomes again progressively thinner until we get our desired thickness of material. That gas bubble in there becomes elongated and flattened. Okay, and then that's our lamination. So lamination, it's a planar defect. It's two-dimensional. Okay. Put an ultrasonic probe on there. Okay, and that sound wave will hit the defect, come straight back. We can be pretty sure that's a lamination. Okay. So fine laminations in plate and in pipe. Remember, it's in the middle thickness, it's in the roll direction, and we find them very easily with ultrasonic testing. Okay, so like I said, blocks are ended, that gets rolled out, and then in service, well, there's our lamination. Okay, so if we had a piece of steel, it's 20 millimeters thick, where the lamination is effectively is you've got two bits of steel which are approximately 10 millimeters thick each. Again, that's our lamination in the middle thickness of the material. So steel structures, major fabrication process involves welding. Some of the problems are associated. So again, in the fabrication process, so incorrect angle of bevel, improper pre or post heat treatment, poor fit up, and wrong welding consumables. So most of this won't be evident in service. Okay, not to worry too much about it. Hydrogen-induced cold cracking. Again, we'll go through this, but don't worry about it. Okay. So hydrogen-induced cold cracking, normally formed in the HAZ after the weld is completed. It may occur almost immediately, hours or even days after the weld is finished. Non-destructive testing is usually carried out after 48 hours if there's a risk of hydrogen-induced cracking. Hydrogen dissolves in the weld pool, permeates through the weld into the HAZ, and it brittles the microstructure. So what does all that nonsense mean? Okay. Let's just do it on the board. But again, it's not something to worry too much about. So, in the first instance, and again, we'll cover this a bit more when we talk about the welding processes. So, in the first instance, you've got butt joint. Okay, always refer to the butt joint before we weld it up. Okay, so this is a single B. And the whole idea of moving this metal is so the welder can get the electrode down into the bottom of the joint, put the root in. Okay, and then we're going to fill it all back up, and we're going to put all the metal back that we've cut away. Okay, so first run, root, and then you have the hot pass, and then you have your filling runs. Okay, and again, depending on the process, the thickness, even the joint position, will dictate how many runs of weld that you fill in. Okay. Once that's welded up, then the idea is that all this just becomes one mess of metal. Okay. If it's been done correctly, of course. Okay, so there you go. So it's all fused together. Okay. So what can happen when we're welding, okay, is we can introduce hydrogen from the electrode into the weld metal. Okay. And what we've got, for all we said, this is one mass of metal. Where the weld metal, parent metal meet, is fusion boundary. Okay. And then just adjacent to the fusion boundary is an area called the HAZ. Okay. So HAZ is the heat affected zone. Okay. So it's part of the parent material which has been heated sufficiently enough to change the grain structure, but it hasn't actually melted. Okay. So the hydrogen that we're introducing into the weld metal, okay, can permeate from the weld metal into the heat affected zone. Okay. And if we looked at that heat affected zone under a microscope, what we'd have is the grains of the steel be like that, quite large. Okay. And the hydrogen would sit in there quite nicely. Okay. While everything's at an elevated temperature, greater than 300 degrees, okay, hydrogen then can diffuse out of the weld metal. Okay. Well, when we reduce that temperature to less than 300 degrees, okay, what happens? All these atoms of the metal move that much closer together. Okay. When they move up, nice and tight, there's nowhere for the hydrogen to go, it can't escape. Okay. And that builds up pressure and effectively causes the material to crack. So you get cracking in the heat affected zone. Okay, and that's hydrogen induced cold cracking. Okay. And that's about as much as you need to know for this. Okay. So again, introduce the hydrogen into the weld metal from the electrode, okay, from the welding consumables. Hydrogen migrates at the HAZ. So at an elevated temperature, hydrogen can escape. Temperature drops below 300 degrees. Everything squeezes up a little bit tighter. Hydrogen gets squeezed, builds up the pressure, causes the material to crack. Okay. But again, it's going to be dependent on lots of factors: the type of welding consumable used, the susceptibility of the material. You know, and obviously we put control measures in to reduce the effects of this hydrogen upliftment. Okay. And usually, like it says there, carry out NDT up to 48 hours after the weld has been completed to look for any hydrogen-induced cracking. Okay. So the cracks we see in service shouldn't be hydrogen-induced cracking, because this is effectively a fabrication. Okay. like I said, so we've spent 5 minutes explaining it. Don't worry about it. Okay. So it's put things in, and I think if they're not explained properly, then we'll, what's the point of putting it in? Okay. So that's our hydrogen-induced poker. Designing out stressors. So again, we'll look at this a little bit more tomorrow. Sorry, Wednesday. We'll look at welding. Okay. So, so there we've got a node. Okay. Usually, when we have a node, draw it this way. You've got your cord and your brace. Okay. So we join the cord to the brace like that, and we've got a weld in that position there. Okay. So our weld is in the highest stress point. Okay. Whereas if we have a cast node, we're removing the weld from that high stress position, putting the weld into a lower area of stress. Okay. Obviously, with the cast node, we've got 3 times the amount of welding to do, though. Okay. So we've got to produce a cast node in the first instance. Then we've got 3 times the amount of welding. So the cost incurred are massive. Okay. So we don't often see a cast node like that. Okay. Although from a fatigue point of view, it would be much better because we're removing the weld from the high stress concentration area. Okay. But, cost wins out. So we end up with our weld in our high stress concentration point. Okay. Shape of the weld as well is also very important. Yeah, and again we'll see tomorrow, or rather Wednesday. So if we have a T joint, so we join a T joint together with fillet weld. Okay, so fillet weld, things like that. Okay, and the fillet weld gets its strength from what is known as its throat thickness. Okay, so we draw a line between the toes like that. Okay, the throat thickness is that dimension in there. Okay. So anything above that green line, okay, that's excess weld metal. It doesn't offer any further strength to the joint. Okay, in fact, the sharper the change in geometry at the toe, so the more of that excess weld metal we've got, then the worse it is in terms of fatigue strength. Okay, so ideally we want a nice, what's referred to as a mitre fillet weld. Okay, but this one would be the absolute least desirable. Okay, to further improve the strength or the fatigue properties, at least, is we can do a concave fillet weld. Okay, so if we have a weld that shape, okay, we're removing the sharp change in geometry and the stress concentrations, but we also end up reducing the throat thickness. So again, to have a concave fillet weld, you would need a much bigger weld overall. Okay, so again, there's always a trade-off between best fatigue properties and the cost. Okay, so ideally we want a mitre fillet weld, okay, which is the best compromise. Okay, but again, we'll talk more on welding that Wednesday. So after we've produced all our raw materials, put everything to size, we've then fabricated it, done all our inspection on our jacket. Okay, and again, during the construction phase, during fabrication, is when the most comprehensive inspection programs are carried out. Okay, so inspection programs last throughout the lifetime of the structure, but the most comprehensive inspection programs carried out during fabrication. Okay. So next stage then is installation. So steel structure is installed in two major operations. The jacket is positioned and piled in. Deck modules are craned into place and commissioned. During these operations, structural damage may occur. So post-installation, baseline survey is carried out. So baseline survey is the first major in-water inspection. Okay. So after we've done our baseline survey, then the normal working life of the structure. So again, we said typically 25 years. Okay. We'll do our in-service inspections based on a 5-yearly cycle. Some items are inspected more often than others. Okay. And again, we said safety critical elements usually inspected every year. Something that's less critical, inspected less frequently. Okay. So a type of defects that may occur during the service life, fouling defects. So that's again dropped objects, and of course marine fouling, coating damage, cracks, erosion, physical damage, and scour. Okay, so we'll look at these. Well, there's a good example of a fatigue failure. Okay. So again, it also shows residual stress as well. Okay, because we can see how far the two components have moved away from each other. So they were perhaps force fitted, welded up. Yeah, and then to me, the crack started on this side here. Okay, and then it looks like it's propagated round from that point. Okay, to about there, and then you can see that bit there. It's quite a raggy edge, so that's our plastic deformation. Okay, so that's showing ductile failure. Okay, so that bit of steel there was originally, you know, the thickness of the cord there, isn't it? Yeah, so the cracks developed, propagated through, and then we've got very rapid failure at the end, and then you can see how far it's moved away. Okay. Same with this one. I think crack initiation point was somewhere around there. Yeah, that thickness of material, same thickness as that. That's the weld. Okay, and then the cracks continued around there like that, and then eventually it's failed and that movement away from it. Okay. The other important thing to note is, you know, before the actual failure occurred, before those two components, there's no evidence of any plastic deformation here. The marine growth isn't even disturbed. Okay, so we wouldn't have known that crack was growing there unless we'd have done some sort of inspection on it. So visual inspection, then MPI, ACFM to establish whether or not we've got a crack-like defect. Okay, well, like I said, obviously it's gone unnoticed. It's got to the point where it's then failed. Okay, because the rest of the material will no longer withstand the load. Okay. So specific types of in-service deterioration. So in the intertidal zone or splash zone, we said we're going to get more marine growth up there. So higher risk physical damage, more aggressive corrosion. Because again, impressed current systems, sacrificial anode systems only work when they are permanently immersed in the electrolyte. So any steel component that's in the water, then out the water, it's out the water but still wet, still water on it, then it's going to just continue to corrode. Okay. Risers. So these carry products, high pressure, temperature. Conductors, conductor guide frames, again subject to pressure and wear. And then caissons, again subject to vibration and wear. And then of course there's always the risk of overloading the structures by installing extra, bigger, heavier equipment. Okay. And again, more equipment put onto a structure, more load we're putting onto it. So again, at the very least, we may increase the rate of corrosion. Corrosion we'll talk about tomorrow. Okay, but you can see again, the results of corrosion there. Okay. So repair to offshore structures. So if a defect is found, down to the engineers, duty holders, engineering department will decide what course of action to take. Defects that might be identified, maybe weld defects, impact damage, fatigue damage, and corrosion. So our repair methods then, so wet welding, being used for over 70 years, but due to the problems associated with it, such as uncontrolled cooling rates, brittleness caused by quenching, lack of sidewall or interinfusion, and hydrogen berittlement. This technique is only used for temporary, non-structural repairs, low-stressed items. Yeah. We do have a better understanding of the process, better consumables. We can do structural repairs with wet welding, okay, but they must be done with, multiple passes. You couldn't just do one weld. Okay. So more advanced hyperbaric welding. So a habitat sealed on the repair site, and the weld is completed in the dry. The TIG welding process, most frequently used, TIG, tungsten inert gas. If you're not familiar with that, again, from Wednesday you will be. Specially qualified weld divers are employed. And then clamp repairs. So we've got two types of clamp repairs, a grout clamp or a friction clamp. So grout clamp, so as you can see, two half shells placed over the repair site. They're quite loosely fitting, and then grout is pumped in between the in the annulus there to effectively form the repair. And then friction clamps. So these are made to much tighter tolerances. Okay. Put over the area to be repaired rather. Two sections are bolted up tightly. Then all the stresses are then channeled through the clamp itself. Yeah. So friction clamp bolted on and manufactured to close tolerances. All repairs are inspected to ensure compliance with the procedures, and the damage register will be paid. Now, okay. So, any questions on that one? Guess it's pretty straightforward, wasn't it? Okay. Anything to do with welding, don't be too concerned with. Again, we'll do a separate lecture on that on Wednesday. Okay, so again, we'll talk about hydrogen cracking, joint design, things like that. Again, so don't worry about that. Okay, so any questions on that or anything else so far?
Just a quick question on the installation.
Yep.
Because on the picture there, so I noticed it's only the legs, upper legs is being flooded. So suppose the members are not supposed to be flooded.
Yeah, I can't imagine the members being flooded. I guess because what you would have is these would be nodes. Yeah. So this would be one open tube, I guess, where they'd be welded to it, so there wouldn't be any water going through those ones either. Okay. So you flood the legs, drop it down onto the seabed, but not between the members themselves. Okay.
Yeah.
Because if we look at that photograph there, and again, that's the same idea. That's a if that was your leg section, that'd be welded to it, and that was originally part of that. So there wouldn't be access in between the two, so you wouldn't get water flowing between the two legs or the two components. Okay.
Yeah. Okay.
Yeah. Anyone else?
Okay.
Okay. So send you this. Okay, so that's the homework just sent by the chat. Okay. You don't need these back. Okay, so don't worry about emailing it to me or anything like that. Okay, so do this one that I've sent you rather than the one on the Virtual Academy, and we'll discuss it tomorrow. They all start off the same. Some quite easy multi-choice questions just to get you warmed up. Okay, so read the question, you know, select whichever answer you think is correct. Okay. Obviously, I don't know whether they're right or not because I haven't read them. Okay. And then there's some short written answers to do. Okay, so you can either find the answers to these in your notes or in the revision notes on the Virtual Academy. Okay, and all these are short answers, you know, a couple of lines. Okay, or even just one line in that respect. Okay, and again, it's just a way for you to go back, look through your notes, and consolidate what we've gone through today. Okay, but like I said, it's for your own benefit. It's not marked. I don't want to see them. Okay, but they do help with, again, just consolidating what we've gone through. Okay, so tomorrow when we meet, we'll do same thing. Always start with the homework. We'll ask if there's any questions from the day before, and then we'll continue with the lectures tomorrow. Okay, so any other questions?
So thank you, Chris. Thank you.
Oh, all right, cool.
Yes, Chris.
So,
Thank you.
yeah, so what we'll do then, we'll leave things there for today, and then again meet tomorrow morning, 9 a.m. UK time, and just go from there. Really, be a bit more of the same, I'm afraid. Okay. All right, cool.
Thanks, Chris.
Right.
Cheers, man.
Thank you very much for
Yeah.
your participation.
Thanks.
Thank you.
See you all in the morning.
See you tomorrow. Yeah.
Thank you very much. Cheers. Bye for now.